Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Okay, great. So I'm really glad to meet you again in my class. And now let's enter the discussion about instruction pipelining. I think that I have discussed this in maybe one of my previous lessons. I don't really remember about that, but okay, even that we have discussed it, it's still a good thing to review it. Okay, so about instruction pipelining. So yeah, as computer systems evolve, their greater performance can be achieved by taking advantages of improvements in technology such as faster circuitry, and in addition that the organization enhancement to the processor can improve the performance. There are some approach that can be used. One of them, which is quite common, is instruction pipeline. So here's the strategy. So instruction pipelining is actually similar to the use of assembly line in a manufacturing plant. Okay, so by laying the production process out in an assembly line, then the products at various stages can be worked on simultaneously, and this is what called pipelining. Okay, because it is as in a pipeline, new inputs are accepted at one end before previously accepted inputs appear as outputs at the other end. So this is a very important. Okay, so let's see the figure that show us how to do a two-stage instruction pipelining. Okay, so here's a simplified view. We have instruction and fetch, and instruction goes to the execute, then it will give the result. But actually, this is an expanded view. So we have instruction, then we have fetch. Some will be discarded, some will wait, and some goes to some will be passed to execute. The execute, some will be look to wait. Okay, some will be passed back, fed back into the fetch, make a new address. Some will be passed as a result. Okay, so here's the explanation. There are times during the execution of an instruction when memory is not being accessed, and this time could be used to fetch the next instruction in parallel with the execution of the current one. Okay, so the pipeline has two independent stages. So the first stage fetch an instruction and buffers it. When the second stage is free, then the first stage pass it into the buffer instruction. And while the second stage is executing the instruction, then the first stage takes advantage of any unused memory cycles to fetch and buffer the next instruction. And this is what called instruction prefetch or fetch overlap. Okay, so in this approach that involves the instruction buffering, it will require more registers. Okay, so this is a drawback. So in general, that the pipelining requires registers to store data between stages. And it should be clear actually that this process will speed up instruction execution. If the fetch and execute stages were of equal duration, then the instruction cycle time would be half. But if we look more closely at this pipeline, which is shown in the figure 12.9b, actually we'll see that this doubling of execution rate is unlikely for two reasons. The first reason is that the execution time will generally be longer than the fetch time. Then the execution will involve reading and storing operands and the performance of some operation. Thus, the fetch stage may have to wait for some time before it can empty its buffer. So this is the first reason. The second reason we encounter is a condition of branch instruction makes the address of the next instruction to be fetched unknown. Okay, here's the point. A conditional branch instruction makes the next instruction to be fetched unknown. Thus, the fetch stage must wait until it receives the next instruction address from the execute stage. And the execute stage may then have to wait again while the next instruction is fetched. Okay, so we can have a clear depiction of how many time loss. Okay, so yeah, it simply cannot show us that this is how. Okay, so here, if the branch is not taken, no time is lost. If the branch is taken, the fetch instruction must be discarded and new instruction fetch. Okay. So while these factors reduce the potential effectiveness of the two-stage pipeline, some speed up actually may occur. And to gain further speed up, the pipeline must have more stages. And let us consider some decomposition of the instruction processing. First, we have fetch instruction. We have also decode instruction. I'll not read the description for you. You can read it by yourself. We also have calculate operands. We also have fetch operands. Actually, they are all fairly self-explanatory. We also have execute instruction. We also have write operand. And with this kind of decomposition into six elements, that the various stages will be of more nearly equal duration. And for the sake of illustration, let us assume that all is of equal duration. Okay, so let us see how this is done. This is the timing diagram, just a sketch for instruction pipeline operation. Okay, so several comments are in order. The diagram assumes that each instruction goes through all 6 stages of the pipeline, and this not always be the case. For example, a load instruction doesn't need a WO stage. Okay, it doesn't need a write operand. Okay, write operand stage. But to simplify it, we just said it, assuming that each instruction will require all these 6 stages. Okay, I have to explain. And the diagrams implies that all the accesses can occur simultaneously. But actually, most memory systems will not permit that. Okay, thus much of the time that memory complete will not slow down. But actually, there are several other factors that serve to limit the performance enhancement. So here's the important note here. If the 6 stages are not of equal duration, then there will be some waiting involved at various pipeline stages as described before for the 2-stage pipeline. And another difficulty is that the conditional branch instruction, which can be invalidated for instruction fetch. Then a similar unpredictable event is an interrupt. Okay, so let's see. Okay, so we are directed to see figure 12.11. Okay, so actually this is how the conditional branch done, which will affect the instruction pipeline operation. So you see that here's the description. Assume that instruction 3 is a conditional branch to instruction 15, that until the instruction is executed, there's no way of knowing. This is the issue that is outlined before, right? Okay, there is no way of knowing which instruction will come next. Then the pipeline, in this example, simply loads the next instruction in sequences and proceeds. Well, actually, when we are discussing before, this branch is not taken and we will get the full performance benefit. Okay, so actually here's the flow chart. 6-stage CPU instruction pipeline. I think maybe you should read this by yourself. And yeah, after we have discussed so far, actually there remain elements that designers still must need to consider. First, at each stage of the pipeline, there is some overhead involved. Okay? Overhead involved in moving data from buffer to buffer and in performing various preparation and delivery functions. Okay. And this overhead can appreciably lengthen the total execution time of a single instruction. Second, that the amount of control logic required to handle memory and register dependencies and to optimize the use of the pipeline increases enormously with the number of stages. And this may lead to a situation where the logic controlling the getting between stages is more complex than the stages being controlled. And another consideration is latching delay, which is it takes time for pipeline buffers to operate and this adds to the instruction cycle time. Let's see, here's the formula to show us the pipeline performance. Okay, the cycle time of okay, the cycle time of instruction is shown as okay as this. Okay, we have tau I, which is the time delay of the circuitry in the ith stage of the pipeline. We have tau m, which is the maximum stage delay. We have k, which is the number of stages in the instruction pipeline, and we also have d, which is the time delay of the latch. So there are some other formulas, which is the derivation, of the previous formulas. I think this is not very important. I will skip this topic. Okay, let's continue to this one. Pipeline hazards. So a pipeline hazard occurs when the pipeline or some portion of the pipeline must stall because conditions do not permit continued execution. And such a pipeline stall is also referred to a pipeline bubble. And actually there are three types of this, which is a resource hazard, data hazard, and control hazard. First, a resource hazard. A resource hazard occurs when two or more instructions that are already in the pipeline need the same resource, and the result is the instruction must be executed in serial rather than parallel for a portion of the pipeline. And this sometimes called a structural hazard. I'll now explain the example. I will go directly into data hazard. But before is that one approach to analyzing resource conflicts and aiding in the design of pipeline is the reservation table. Maybe we'll get to see this later. Okay. The second type is data hazard. So data hazard occurs when there is a conflict in the access of an operand location, and in general terms that we can state the hazard in the two forms. First one is two instructions in a program are to be executed in sequence and both access a particular memory or register operand. If the two instructions are executed in strict sequence, that no problems occurs. But if the instructions are executed in a pipeline, then it is possible for the operand value to be updated in such a way as to produce a different result that then will occur with strict sequential operation. So this is a problem. And there is also an example that I'll leave for you to read by yourself. And actually, there are also three types of data hazard. The first one is read after write, which is true dependency. The second is write after read, which is anti-dependency. And write after write. Why all of this is written RAW? This is RAW, this is WAR, and this is WAW. Maybe the book is there is some mistype in the book. Okay. And yeah, this is called output dependency. I'll not dive into greater depth for this topic because actually we will not make use of this. Okay. Then the third type is that control hazard. So for a control hazard, that is also known as a branch hazard. It occurs when the pipeline makes the wrong decision on a branch prediction and therefore brings instruction into the pipeline that must subsequently be discarded. Okay, so because we have seen control hazard before, then there must be a question. How to deal with branches? Okay. So one of the major problems in designing an instruction pipeline is assuring a steady flow of instructions to the initial stages of the pipeline. And the primary impediment is the conditional branch instruction. Okay, conditional branch instruction. So there are actually a variety of approaches for to deal with conditional branches, such as multiple streams, prefetch branch target, loop buffer, branch prediction. Also, we have delayed branch. Let's see one by one. First, multiple streams. A simple pipeline suffers a penalty for a branch instruction because it must choose one of two instructions to fetch it and may make the wrong choice. So a brute force approach is to replicate the initial process of the pipeline and allow the pipeline to fetch both instructions, making use of two streams. But there are two problems. First, with multiple pipelines, there are contention delays for access storage and to memory, and additional branch instruction may enter the pipeline before the original branch decision is resolved. Okay, but this can improve performance. Okay, the second one, prefetch branch target. So when a condition branch is recognized that the target of the branch is prefetched, then in addition to the instruction following the branch, and this target is then saved until the branch instruction is executed. And if the branch is taken, then this target has already been prefetched. The third one is a loop buffer. Okay, so this is a small, very high-speed memory maintained by instruction fetch stage of the pipeline and containing the n most recently. Okay, so here's the important thing: containing the n most recently fetched instructions in sequence. So if a branch is to be taken and the hardware first checks whether the branch target is within its buffer, then if so, the next instruction fetches from the buffer. There are three benefits here. There is outlined in this book. So with the use of prefetching, then the loop buffer contains some instructions sequentially ahead of the current instruction fetch set, instruction fetch address. Thus, instruction fetch in sequence will be available without the usual memory access time. Then if a branch occurs to a target just a few locations ahead of the address of the instruction, then the target will be already in buffer. And this is useful rather than come occurrence of if then else sequences. And the third one is that this strategy is particularly well suited to dealing with loops or iterations, and hence the name is loop buffer. Okay, so if the loop buffer is large enough to contain all the instructions in a loop, then those instructions need to be fetched from the memory only once and for the first iteration. So for subsequent iteration, they already in the buffer. So this is the advantage. Okay. Okay, maybe this is the last one for today's video. Branch prediction. So there are various techniques can be used to predict whether a branch will be taken. Here's 5 that's pointed in the book. So first one is predict never taken, predict always taken, predict by opcode, taken not taken switch, and branch history table. So the first three, predict never taken, predict always taken, and predict by opcode, are static. They do not depend on the execution history up to the time of the condition branch instruction. Where the later two approaches are dynamic, that they depend on the execution history. The first three approaches, the predict never taken and predict always taken, are the simplest. And this either always assume that the branch will not be taken and continue to fetch instructions sequence, or they always assume that the branch will be taken and always fetch from the branch target. And the predict never taken approach is the most popular one. Okay. For dynamic branch strategies, it attempts to improve the accuracy of prediction for recording the history of conditional branch instruction in program. And these bits are referred to as a taken, not taken switch that direct the processor to make a particular decision the next time the instruction is encountered. And typically, these history bits are not associated with the instruction in main memory, but rather they are kept in temporary high-speed storage. Okay? And one possibility is that to associate this bit with any conditional branch instruction that is in a cache, and where the instruction is replaced in a cache, its history is lost. Then any other possibilities that to maintain a small table for recently executed branch instruction with one or more history bits in each entry, and the processor could access the table associatively, like the cache, or by using the low order bits of the branch instruction. Okay, so here's the flowchart. I want you to read it by yourself. Okay, but there's a one drawback that we use history bits that if the decision is made to take the branch, that the target instruction cannot be fetched until the target address, which is the operand in the conditional branch instructions decoding. Okay, and branch history table is a small case memory associated with the instruction first stage of Python. This is another state diagram that maybe you want to see. Okay. Okay, this is the last one, delayed branch. So it's possible to improve pipeline performance by automatically rearranging instruction within a program so that branch instructions occur later than actually desired. And we will see this later in the next chapter. Okay? Yeah, I think that's enough for today. Okay, and yeah, before I end this lesson, here's a little quote for you from Henry Ford that the unmemorable mistake is the one from which we learn nothing. Okay, and that's all our lesson for today. Thanks for watching, and here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https colon/science with xyz.unux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.